Welcome back, everyone, to this lecture on encoding text data for natural language processing with PyTorch. In this lecture, we're going to focus on reading in the text data and then encoding it in order for our network to understand. Networks cannot understand just raw text information, so what we need to do is encode that text information. So since we're going to be working at a character level, each character will be assigned a value. So for instance, A is 0, B is 1, C is 2, and so on. And keep in mind, when we say character, we don't just mean letters, but we also mean things like a new line, a space, or punctuation. Those all get assigned their own unique integer value. Then we need to one-hot encode these values as well. For example, if we're dealing with the character A and its value was assigned 0, then we have an array which has as many spaces as there are unique characters in our text data set. And then we provide a value of 1 for the correct index position that corresponds to that original character's assigned value. So A0, then at index 0, we have a 1. For example, then with the letter C, it gets assigned the value 2. So at index position 2, in this one-hot encoded array, we assign a value of 1. Okay, let's go ahead and see how we can do this in practice with Python by jumping over to the Jupyter Notebook. Okay, first we're going to begin with some basic imports. We'll import Torch, and then later on, in order to build our networks, from Torch we'll import NN, and then import torch.nn.functional as capital F. And just in case we need to use NumPy or matplotlib for any plotting, we can always say import NumPy as NP, import matplotlib.pyplot as PLT, and depending on what version of the notebook you're using, matplotlib inline. Okay, so nothing new there. Let's go ahead and get our text data. Say with open, and this will then automatically open a file. Inside of our data folder, we have a file called shakespeare.txt. You'll go ahead and open it with the code R, which stands for reading. And this particular file has an encoding of UTF-8, so pass that in as a string. And then we can decide what we actually want to call this variable. So we'll say as f, which basically this line just says, go ahead, open up this text file, read it, it has this particular encoding, and then make sure we don't have an extra string there, save it as the variable f. So this is now a block of code where inside of this block, after this colon, anywhere I reference f, I go ahead and read it. We'll just read in the entire text file by saying text is equal to f.read. So go ahead and run that, and if you ran it correctly, text, if you take a look at the type of it, is just one giant string of all this Shakespeare text. And typically, when you're working with text generation, the larger the data set, the better. Keep in mind though, larger data sets take longer to train, but it gives the network more examples of different situations to learn off of. Let's go ahead and review what this text actually looks like. So we'll take a look at the first 1,000 characters of this text, and you'll notice that there's essentially these \n's, which stands for new lines, as well as a bunch of spacing, and then numbers, and then the actual beginnings of the sonnet. So what does this actually mean? Well, it means that this is the raw string, but if we want to print this out to see what it would actually look like, it looks like this. So we can see here that there's those new line breaks in order to kind of separate out the sonnet, as well as spacing with numbers. So these are the sort of things that we're going to hope our network learns from, as far as the overall spacing of these sort of brackets or sections of text. So how long is our actual text? Well, we can check this out by saying length of text. And we can see here we have around 5 million characters, or maybe around 5.5 million characters inside this text. So now let's get on to encoding the entire text. We're going to base this off a character level, which means what we need to do is figure out all the unique characters inside of this text. We can do this easily by simply saying all characters is equal to, and then just pass in the text into the set command. And what this does, if we take a look at this set, it just returns back all the unique characters. And by characters, this also includes things like punctuation, numbers, capital letters, and then lowercase letters as well. So here are all the unique characters, and if we check the length of this, there are 84 unique characters inside of our text. So what we're going to do is we're going to create two objects, a decoder and an encoder. The encoder will take in a character and then return back its encoded number. The decoder will do the opposite. Given a number, go ahead and return back its corresponding character. So it's typically easier to actually build the decoder first. So recall that a decoder takes in the number value and then transforms it into the letter. And this is essentially just a lookup dictionary. So what we're going to do here is we'll just say create a dictionary by enumerating all those characters. So enumerate all characters, what that essentially does is if we take a look at that, we can actually then cycle through it. We'll say for pair and enumerate all characters, print out that pair, and then it just assigns a number for each of these characters. So notice here we have this number and this character, etc. So that's all enumerate is doing. So then we're just going to perform and cast this as a dictionary in order to create our decoder. So then if we look at our decoder, it's essentially a key with a number with a corresponding value of the character. And now for the encoder, we want to do the opposite. So the encoder object is going to take in a letter and then return back its corresponding number. So the encoder, what we can do is we can use essentially kind of a dictionary generator here. So say go ahead and say character index for that tuple pair of index comma character in decoder items. So we run that and we take a look at our encoder, and it's essentially now the opposite. And you should always double check to make sure that your decoder and your encoder are actually matching up the correct character to the correct number position. So here we can see that the character of 8 or the character of ampersand both have 0 and 1. So if we come back down here to the encoder, we can see here that the character 8 corresponds to 0, the character of ampersand corresponds to 1, and so on. So they're matching up, which makes sense given the way that we built this out. So let's actually show you what the encoded text would look like. What we're going to do now is we're going to take in, if we go ahead and comment some of this out to save a little bit of space, we're going to take in all this text that we originally had and then encode it so that it has a numerical information aspect to it. We will say encoded text is equal to, and we're going to cast this as an array so it's easier to work with later on. And we're going to use a list comprehension, which basically says, say encoder, square braces, because this is a dictionary lookup. Encoder is just a dictionary. So encoder of that character for character in text. So what are we doing here? This line right here essentially builds out a list of all the encoded characters for the character in the text. And encoded here is just a dictionary, which is why we're using square braces here. Go ahead and run that. This may take a little bit of time depending on your computer, but after a while you should be able to then say encoded text. And let's just go ahead and look at the first 500 characters here. And we can see the first 500 characters, it's 13, 27, 27, 27, etc., and then all the encoded text. So you might be wondering, well, what's going on with all these 27s in a row? If we take a look back at the original text, recall that there's a bunch of spaces in a row. Let's confirm this by saying decoder, pass in 27, and you notice that that's exactly what it is. It's a space. So it makes sense that wherever there's a 27 here, which is probably going to be one of the most common numbers shown, you can see it all over the place. That's essentially just indicating a space. Okay, now that we have our encoded text to values, the last thing we need to do is create a one-hot encoder function for this. So I'm going to scroll down here, and I'm going to create a function. So as previously discussed, we need to one-hot encode our data in order for it to work for a network structure. So we'll say def, and I'm going to create a function called one-hot encoder, and we're going to make it a little more generalized because we're going to be one-hot encoding batches later on in this notebook. So we're going to say take in any piece of encoded text, and also then take in the number of unique characters. And the reason I'm actually providing number of unique characters as a parameter into this function is that way you can use this for your own text data. So later on you'll see that essentially what you're going to be able to do is change this text file to whatever text file you want to play around with, and all the code will work the same. Okay, so what we have here is encoded text, and encoded text what that's actually going to be later on is that just a batch of encoded text. So keep in mind, it's not going to be all our encoded text, it's just one batch at a time. And when I say encoded, I mean encoded to this number format, not one hot encoded. That's what this function is going to do. And then the other thing, the number of unique characters, essentially what that is it's just the set on the actual text. And it's actually the length of the set. So how many unique characters do you have? So what do we need to do here? So this method, I got it from a Stack Overflow link, so you can always check that out. I linked it for you. But basically, it's just a Stack Overflow post that's telling you how to take an array like 103 and convert it to something that looks like this. So that's where I got this code from. And I would always encourage you to do the same. It's most likely that if you're working on a problem, someone else has worked on something very similar. So the first thing we do is create a placeholder for all the zeros. So essentially just creating a bunch of zeros at first in order to later on fill them in with ones in the correct positions. So we'll say that one hot is equal to np.zeros, and the size we're going to use here is encoded underscore text dot size, and we're going to assume that it has dot size available because encoded text is going to be a numpy array, which it is given the way we're creating them up here. So we'll have encoded text as a numpy array, so that np0s is encoded underscore text dot size by the number of unique characters. So now we have all these zeros, and we have this placeholder. Next, what we need to do is convert the data type for later use of PyTorch. So if you don't convert it to 32-bit float, you'll get some errors later on. So we'll say one hot is equal to one hot as type, and say np.float32, which is later on the precision that PyTorch wants. So we have these zeros, and they're all now encoded to 32-bit float precision. Next, we want to do is just use fancy indexing, which is kind of the official NumPy term, to fill in the ones at the correct index location. And again, essentially just using that code from the Stack Overflow post, what we're going to say is go ahead and grab one hot, and then say np.arrange one hot dot shape. Go ahead and grab the first number in that shape, so essentially number of rows, and then what we're going to do is say the encoded text, and we will flatten it out, and we'll set that equal to 1.0. Okay, so what is this actually doing? Recall that one hot is essentially just zeros to start out with, but what we're doing here is we're setting up this range of numbers, one hot encoded, shape 0, and then we're going to go ahead and grab the encoded text and flatten it out. And essentially, that's going to set that wherever that index position happens to meet up, set it as 1.0. So what that does is, for instance, if we have 27, it goes ahead and finds the 27 index location position and sets it to 1.0. And this may be a little hard to imagine with such a large data set, but if you take a look at the link that we provided for you in our lecture notebook, you can see here that the logic makes a lot more sense when we're dealing with something just smaller. So I encourage you to check out this kind of smaller example, which is providing the one hot encoding. So we're going to come back to our notebook here. And then finally, we need to reshape this so that it matches the actual batch shape. So we'll say one hot is equal to one underscore hot. And we're going to reshape this. And the way we can do this is by saying an asterisk encoded text dot shape by number of unique characters. Because technically later on we want to be able to play around with the batch size. That's why we're passing it in based off the encoded text dot shape. And then once that's done, we'll go ahead and just return one hot. Okay, let's go ahead and test this out and make sure everything's working. And create a really simple array. We'll just say np array, and this will say 1, 2, 0. So this is my example array. So I check out my array. It has 1, 2, and 0, which means the actual number of unique characters is 3, because there's 0, a 1, and a 2. So I'm going to call one hot encoder. I'll pass in my array, and say there's 3 unique characters there. I go ahead and run this, and it has now one hot encoded it. So now I have this little batch here. So what's going on here? At index 1, for the first item, I have a 1. At index 2, I have a 1. And then at index 0, I have a 1. Okay, so now we successfully encoded our text. We read it in. Now we have a decoder and an encoder. The decoder will come in handy when we actually want to predict text and write it out, because really what we're going to be predicting is just these index locations with some probability. And then we also created our one hot encoder, which we'll use later on with the batches. Coming up next, we'll go ahead and show you how to create training batches for the text data. I'll see you there.